Hey, I'm just going to record a very quick video explaining how Merkle puzzles work. Now, Merkle puzzles solve that fantastically interesting problem, which is called key distribution. And it turns out in security, we have all these fantastic ways to do encryption, but they all rely on a key. And it's a very hard problem to get a key to somebody safely and securely so other people can't see it. Um, you could encrypt a key, but then you're trying to do encryption in the first place. So Merkle puzzles is one of these approaches that we use to solve the key distribution problem. There's a few other ways, like we use RSA, also known as asymmetric encryption. We also use the Diffie-Hellman key exchange, very cool. We use the public key infrastructure, which is a combination of RSA. And we also use Merkle puzzles. You'll find out that actually they're not very practical Merkle puzzles, so we don't actually use them. But they're a very cool concept to let you understand the problem of key distribution. So what is a Merkle puzzle? Let me explain that on this wonderful next page. Merkle puzzle is this. You start off with a little box, right? And these can be whatever you like, little envelopes, little packets, whatever you like. I'm just going to model them here. In fact, I've drawn far too many lines. Let me, 1, 2, 3, 4. I'll just draw another. Excellent. Cool. And in here, what you do in each of these little boxes is you write an identifier, right? You write a little identifier and a key, right? And the identifier might be cheese, and the key will be like a normal encryption key. So you get 9567K. The next one, you'll write an identifier, maybe dog, and then a key. The key will be like what keys normally look like. And you might have cat, ID, this one will be pizza. Oh, these need keys. Blah, 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 the key. Blah, 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 blah. ID, oh, what one haven't we used? iPad, and then the key. Blah, 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 blah. And what you do is you generate these lists of all these things. And for each one of these little packets, you just use your red pen to encrypt it. So I'm going to take that first little packet, I'm going to encrypt it. You take the second one, I'm going to encrypt it. And I use a different key for each of these, but I just encrypt each of them, right? And I've got all these packets here now. And I say to anyone that wants to communicate with me, what I do is I make available all of these packets here. I say 1, 2, I've got 1, 2, 3, 4, 5. I've got 5 packets, but you might have 10,000, you might have 1,000,000, and you said everybody, anyone who wants to talk to me, I'll give you all these encrypted packets. Now, if you want to talk to me, your job is to grab one of these encrypted packets and pick one at random. You might pick this one. And your job is, it's encrypted, that red writing is encryption. And your job is to brute force it. It'll take you, a second, maybe half a second, but you just go through all the potential options there are for this one that when I encrypted it, and just decrypt it. And when you decrypt it, well, you'll do this. It'll disappear, right? You'll be able to see. And inside the packet, there'll be the ID and the key. Now remember, key distribution is what we're trying to do. So here you go, you've got a key. So you can do encryption with me and we can do encryption, which is awesome. But how will I know which key you're using? Because remember, I have 1, 2, 3, 4, 5, but I could have 10,000 of these. The way you let me know which key you're using is by yelling out the word pizza. So you say, I'm using the key that's associated with pizza. And I go, oh, pizza. So I go to my little list. I have a little list of here. It's got all these words here and all these keys here. And I look up pizza. And there is the key there. So I just use this key here. And then we can start communicating, which is really awesome. Now, you might say, hang on a second, how is that secure if you're just passing the key out in public? Well, that's right, we are passing it out, but it is encrypted. So if you're a good guy just wanting to communicate with me, you do need to do some brute forcing. You need to brute force one of these boxes here. But if you're a bad guy, all you're going to hear me yell out is the word pizza. You're not going to know which of these packets contains the word pizza. So in order to find out the key, because the key is listed down here, you're going to have to go through each one of these packets, brute forcing them. And although in my example I only have 5, it's quite possible that you could have as many, let me just draw this, you could have as many as like 10,000. We could have 1,000,000 times these things. And the way this works, if you start off with the first one and brute force it, how many you're going to have to go through before you find the one that says pizza? Well, you know, you'll let me do that. I can do that with this pen. You'll start with the first one and you'll brute force it. It'll take you 2 seconds, and you'll brute force it and you'll open it and it'll say cheese, and you go, damn it, he used the one pizza. So that's all right, no problem. I'll just start brute forcing this one, and you go to all that work and you'll open it up and say, dog, damn it, it said pizza. So I'll keep going. I'll go to this one. I'm just going to work down the list of all these ones. It's got to be one of them. Open it, cat, damn it, it's meant to be pizza. So keep on going, and I'm going to go this one. And blip, aha, pizza. There it is. I just erased it. Pizza. Aha, I found it. So now I know which key he's using for his communication, which is this one here. Now, on average, sometimes I might get lucky. Sometimes pizza might be the first one, and sometimes, if I'm really unlucky, it might be the last one. But on average, it's going to be, I'm going to find it halfway through. It's kind of like if I said pick a number from 1 to 10, and I tried to guess it, 7, 8, 9, 10. You know, if I guessed it, pick a number, maybe you picked 8. It's going to take me on average, you know, halfway through before I actually pick that number. And the same is here. And the kind of maths for that is, killed my line there. The maths for it is that if you have 10,000, let's say we have 10,000 options, on average, I'm going to find it halfway through. So on average, I'm only going to need to search 5,000 of them before I get it. Because sometimes I get it on the first time, sometimes I get it on the last time, but on average, I'm going to get it halfway through. So that is the basis of Merkle puzzles. And the security is in the fact that the bad guy has to do a lot more work. If I just want to communicate with this person using Merkle puzzles, I just have to brute force one, maybe cheese, or maybe the pizza one. But if the bad guy wants to find out which key I did, he's going to have to, on average, do half of all these keys. He's going to have to brute force half of them before he gets to pizza. So that's the idea of Merkle puzzles. And let me answer a Merkle puzzle type question. So here is a Merkle puzzle question. I'll just move my head down here. So you're going to use a system based on Merkle puzzles to allow other people to communicate with you securely, even if you've never met or shared a secret before, which is the problem of key distribution. You encode 1,000,000 messages. So let me write this. I'm just going to draw this as I do it. Back to our puzzles. 1, 2, 3, 4, 5. So I'm going to encode 1,000,000 messages. 1, 2, 3, 1, 2, 3. That's that many of them. Each consisting of a different 20-character English phrase. So that's the ID, which might be pizza. It's 20 characters. And a different 80-bit Merkle key. So the key here is blah, 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 blah. It's 80 bits. Cool. Now, each of the messages will be encoded with a different 40-bit Merkle CDMF key. So this whole packet here is encrypted with 40 bits. So to brute force it, I'm going to have to brute force, on average half of that. So I'm going to have to do 39 bits of work on average. So if somebody has a system which can decode a CDMF cipher into plain text using a given 40-bit key in a billionth of a second, roughly how many seconds will it take them on average to discover a Merkle key used to privately communicate with somebody? So on average, which is an important thing to remember. Give your answer in digits only, round to the nearest power of 2, etc., etc. So let's do that wonderful maths here. So what are they going to have to do in order to brute force my password? Well, remember, like before, these were all red. So what they're going to have to do is they're going to have to start with the first one, right? And they're going to have to brute force the first one. Now we know it's a 40-bit this whole red thing is encrypted with 40 bits of key. Now, on average, remember when something has 40 bits, we get it in half the time. So let's just do that now. So the amount of work I'm going to have to do is I'm going to have to do half. So the total amount of work, right? So it's a total number of things I'm going to have to brute force is 2 to the 40. And then I'm going to have to do half of that. So 2 to the 40 means I'm going to have to brute force 2 to the 39 potential passwords before I get it. But there's another way of writing that. Remember when talking about bits of security, it just means 39 bits of work that I need to do. 39 passwords, not bits of work. What are keys? 39 bits of keys So, very complicated way. It means I'm just going to have to do 2 to the 39. If that makes sense. Now, I'm going to have to do that. There are a million of these. So on average, I'm going to find it halfway through. So that means I'm going to have to do 500,000 bits of work, right? So I'm going to have to brute force one of these rows. I'm going to have to do that 500,000 times as I go down this line. So I'm going to have to do this. This is brute force 1 Merkle puzzle on average. And then I'm going to have to multiply it by, well, the average, the number of Merkle puzzles divided by 2. So let me do that. So I know I want to write this as a power of 2 number. So what's a million as a power of 2 number? Well, we know that 2 to the 20 is approximately equal to 1 million. So half 2 to the 20 is 2 to the 19. So I'm just going to write that down here. 2 to the 19, which is, half of 1 million encrypted puzzles. And of course, I'm only having to search half of them because on average, I'm going to find it halfway through. So that's that. I'm going to brute force 1, and I'm going to have to do that. Cool. So the total amount of work I'm going to have to do, total number of brute forcings I'm going to have to do, is whatever this works out to be, which is add these two numbers here. Oh golly, whatever that works out to be. It's like 60 minus 2 is going to be 2 to the 58. So I have to do 2 to the 58 brute forces, right? Let me just make some room. Not very much room. 2 to the 58 brute forces. I'll put my face over here. Now it says here I have a computer that can do 1 brute force. Sorry, it can do 1. Yeah, it can. What can it do? It can decode a ciphertext into plain text, given a key. Yeah, given a key, in 1 billionth of a second. So that's basically saying that we can do 1 billion guesses per second, right? Because in order to guess one attempt, we're going to have to start with the first possible key, then we go to the second possible key, yeah, and each time we'll encrypt it and compare it. So that essentially means that we can do 1 billion guesses per second. So if we can do 1 billion guesses per second, I think people get confused with this quite a lot. Let's imagine I live in an alternate universe where I have 100 pizzas, right? And I'm a very hungry person, so I can usually eat 5 pizzas per hour. If I said to you, how long would it take Adam to eat all the pizzas? Well, you go, that's easy. Let me just do this in a little box over here. You just take the number of pizzas and you put it over how many you can eat a second, right? So you go 100. There are 100 pizzas to eat. And it takes him 5 he can eat 5 pizzas per hour, well, you just, you cancel that, it becomes 100 over 5, it becomes 20 hours. That's how long it takes Adam to eat it. And it's exactly the same when you're brute forcing things. So like I said up here, we have 2 to the 58 brute forces we have to do. And we can do 1 billion guesses per second. So 2 to the 58 pizzas and 1 billion pizzas can be eaten a second. Let me just rewrite this 1 billion in power of 2 number. So what is it? We know that, where did I do that before? We know that 2 to the 10 is equal to 1024. 2 to the 20 equals 1 million, approximately. And 2 to the 30 equals 1 billion, approximately. So I can rewrite this as 2 to the 30 guesses per second. So just like we did in the pizza example over here, we just say the number of things to brute force divided by how many we can do per second. So 2 to the 58 over 2 to the 30, so this is guesses. Or maybe a better word is attempts, right? We can do 2 to the 30 attempts per second. So we just do that maths there. So the way we do this maths is we just subtract the exponents there. And, oh golly, what is it, 28. So the answer is 2 to the 28 seconds. Give your answer in digits only and round to the nearest power of 2. Right. So if I wrote it as that many seconds, I don't know, 56. So 2 to the 28 seconds. How many seconds is that? Let me pull in my universal calculator, known as Google. 2 to the 28. So it's that many seconds. Let me just check the question here. Give your answer in digits only. Round to the nearest power of 2. I thought it was 70 seconds. You'd enter 60. Okay, so what's the nearest power of 2 number there? Well, that is going to be a power of 2 number, isn't it? So I can just write that answer there, which is, bring that page here. That is 2, 6, 8, 4, 3, 5, 4, 5, 6. That many seconds. So that looks like a big number, and that calculation is right. But that is how you would figure this question out here. So I hope that helped. Yeah, good luck.